hello. My name is Oliver. I'm presenting our work, Providence, an efficient and secure ballot polling risk-limiting audit. This is joint work with Poorvi, Vora, and Filip Zagórski. I did this work while at GW, and I'm now about to start my PhD at UCLA. So what do we want in election security? The most obvious answer to this is that we want the right winner, but a better answer is that we want the right winner and strong evidence that they are in fact the right winner. And in particular, we would like the system to be software independent. So we don't want undetected changes to software, as we just saw in the previous talk, to create undetected changes in the outcome, whether it's due to configuration errors, bugs, or hacking. And so one approach is to use paper ballots, then scan the paper ballots with electronic scanners and get the tally efficiently this way, more efficiently than hand counting, and then perform compliance audits and tabulation audits. So compliance audits confirm that the paper trail is intact and secure, and then tabulation audits draw a small random sample of the paper ballots to confirm that the reported outcome is consistent with the small sample. So in this work, our contributions are a rigorous tabulation audit, a risk-limiting audit called Providence, which is the most efficient and secure of its kind, an open source implementation of Providence, which is included in RLA, which is the most popular audit software, a description of the pilot use of Providence in the city of Providence, Rhode Island, its namesake, in 2022, and a comparison of this audit with other ballot polling RLAs under new simple workload models. So here's some background. First, an RLA begins with the assumption that the compliance audits were successfully completed. And then a risk-limiting audit with risk limit alpha is a tabulation audit that, if the reported outcome is wrong, will detect and correct this error with probability at least 1 minus alpha. And so alpha is an error measure, and smaller alpha is good. And the stopping probability for a given sample is the probability that, given the reported outcome is correct, the audit confirms this result successfully. And so larger stopping probabilities are good. So we focus on ballot polling RLAs, a specific type, and now I'll describe the process of a ballot polling RLA. You begin by choosing a round size, n. You then sample those n ballots uniformly at random using a pseudorandom number generator, and then you manually interpret those ballots. Then you compute the stopping condition, which is a function of the manual interpretations. It outputs one of two things, either undetermined, which means you can proceed to another round, drawing another, choosing another round size and then drawing more ballots. Or at some point when election officials decide to, you can proceed to a full hand recount of the ballots, which doesn't contribute to the risk because you'll count all of the ballots and reveal the underlying distribution. Or the stopping condition outputs correct, which means you've confirmed the result and you're done. So I will describe, before getting to Providence, two existing ballot polling RLAs. The first is Bravo, which is known to be the most efficient RLA, meaning that it requires the smallest expected number of ballots when the reported outcome is correct, when ballots are sampled one at a time, and so this is called a ballot by ballot audit. But in real audits, you draw many ballots at once because it's much more efficient to do so, and this is called a round by round audit. MINERVA is a more recent RLA designed specifically for round by round use. And it's more efficient as a consequence. So in a first round chosen to give a typical 90% probability of stopping, MINERVA requires 50 to 80% as many ballots as Bravo. However, MINERVA is only proven to be risk limiting if all round sizes are predetermined before the audit begins. So here are the problems that we address. The first is that the predetermined round sizes give inflexible audits. In particular, it might be more efficient to choose future round sizes as a function of previous samples. And the second is that existing workload measures don't capture this cost of a round. We are unaware of any RLAs that actually draw a single ballot at a time, and so we address this as well. So here's our work. We begin by introducing an adversary in RLAs. To do so, I need a slightly more technical definition of what an RLA is. So an audit A is an alpha risk-limiting audit if for samples X in the sample space. The probability that the audit outputs correct, given the null hypothesis, is at most the preset risk limit alpha. Here, the null hypothesis H0 corresponds to the incorrectly reported outcome closest to the reported outcome. And so in the two candidate case that I'll be dealing with in this talk, that's a tie. And so the goal of the adversary is to increase the true risk above the risk limit. In particular, the probability that the audit output's correct given the null is more than alpha. So we deal with adversaries who have control over the round sizes, so they're choosing round sizes, and we define two. So the first is the weekly round choosing adversary, who has access to parameters of the audit, like the risk limit alpha, the reported proportion of votes for the winner under the alternative and null hypotheses, PA and P0, and the ballot manifest, which is a list of all the ballots and their locations for sampling. And luckily, both Bravo and MINERVA are secure against the weekly round choosing adversary. However, a strongly round choosing adversary is one who has access to all those same parameters and additionally has access to all previous samples. So here I'm imagining that they're choosing the jth round size, n sub j, and they have access to all the previous round sizes, n1 all the way up to nj minus 1, as well as the samples drawn in those rounds, so the number of ballots for the reported winner found in the samples, which are k1 up through kj minus 1. And so Bravo is again secure against a strongly round choosing adversary. However, MINERVA is not known to be secure against the strongly round choosing adversary. And so this is what we address with Providence. So to describe Providence at a high level, I'll first briefly describe Bravo and MINERVA. So Bravo deals with the probability distribution over this value k, the number of ballots for the reported winner found in the sample, conditioned on each of the two hypotheses. So here's an example of a first round where the sample size is 100, and the green distribution corresponds to the alternative hypothesis, the red distribution corresponds to the null hypothesis. And then suppose we drew 62 ballots for the reported winner. Bravo looks at the ratio of the probability of observing this particular value 62, and it looks at the ratio of those probabilities, so the green point over the red point, or x. And it then applies a threshold. So if that ratio is sufficiently high above the fixed threshold, it confirms the result, it stops, outputs correct. And if it's below the threshold, it does not. It outputs undetermined. Now, MINERVA looks at the exact same probability distributions, but instead of placing a threshold on the ratio of the points observed on the distribution, it places a threshold on the ratio of the tails. Now, this is still risk limiting, so that's good. But it's also nice that this is more efficient because the tails are always greater than or equal to, the ratio of the tails is always greater than or equal to the ratio of the points. And so you will be above that threshold more often or for more values of k. So Providence also uses the tail ratio idea, which means that it gets the efficiency that MINERVA has as well. But the difference lies in how the escalation between rounds is handled. So MINERVA proceeds by looking at the distribution for, in this example, I'll stick to just the second round. MINERVA looks at the distribution over the values of K2 and that the audit didn't stop in the first round, which in particular is that K1 was less than or equal to K-min, the minimum number of ballots required for the audit to stop. And so the way that you compute this distribution is by doing the convolution of the distribution we were just looking at, but lopped off at that value K-min with the new binomials for the marginal draw. So this example we're drawing in the second round just an additional 50 ballots. The problem with this convolution approach that MINERVA takes is that it implicitly assumes that the value N2 is going to be the same regardless of the observed value K1, which is exactly the problem of MINERVA. So the way that Providence proceeds is by looking instead at the distribution over the values of K2 and that the particular value of K1 was observed. And so in our picture, this is now just a product instead of a convolution where on the left, we just look at the particular point that was observed. So in the picture, it's the blue dots. So if you drew 53 in the first round, we just multiply by those corresponding probabilities. And so this no longer has that problem of the implicit assumption about N2. So Providence has the following two properties. The first is that it's risk limiting in the presence of a strongly round choosing adversary, which is what we wanted, and additionally the weakly round choosing adversary as a consequence. And its efficiency is comparable to MINERVA, which there are more details in the paper we show through simulations. And now we'll do one example with workload estimates from the 2016 presidential contest in Virginia. The margin was about 5%. And so we do an experiment where we run 10,000 simulations, where every single round size in the simulations is chosen to give a desired probability of stopping. In fact, we do so for a range of stopping probabilities, and that's what's shown on the x-axis here. And as you can see, the y-axis shows the total number of ballots on average across the trials for each of these stopping probabilities. And so as you can see, for smaller stopping probabilities, you also have fewer total ballots on average, which is exactly consistent with the fact that Bravo in the ballot by ballot case, drawing one ballot at a time, is already known to be most efficient. And so this exactly shows why just using the number of ballots or something linear in the number of ballots isn't sufficient as a workload estimate, because we don't actually want to draw one ballot at a time. And so here's a simple way to introduce a cost per round, just a linear cost per ballot and a linear cost per round. So here, EB is the expected number of ballots, ER the number of rounds, CB the cost per ballot, and CR the cost per round. And now if we look at that exact same example, but instead on the y-axis we plot the workload function, here we just take CB to be 1, so one ballot is one ballot, and then CR, the per round cost, is 1,000. And you see that all of a sudden, for small stopping probabilities, the workload is actually much higher, because if you have a small stopping probability, it takes more rounds on average. So there's more like this in the paper, but this is just an example. So in conclusion, Providence is efficient like MINERVA, but also flexible like Bravo. We introduce workload models accounting for the cost of a round. In the paper, we also discuss other round size considerations like misleading samples and per precinct costs. We describe its pilot use in the city of Providence, Rhode Island. And Providence is implemented in RLA, which is the most commonly used RLA software. And that's it. Thank you.